So therefore, today's discussion is on the applied side of these theoretical models. So far, you have gone through uh, the theoretical side, that how we have built up those models and what results they are expected to give you. Okay. So today's discussion is on application of financial models. You can call them financial forecast models. And risk management. And one more thing I would like to say here, that next week topic is also very important, right? And there I'll be giving you the explanation of those risk management models using which we do our PhD and MS thesis, right? So our MPhil students, those who complete their research work on the real life data, they use those risk management models. Okay, so that's why I would say that don't miss next week lecture as well. And all these are practical things. So the application of two models, we will see today that how we can make a forecast on a real life data and how we try to find out the risk structure of this practical data. But before that, you need to understand two important facts. One is that the stock returns are considered to be a random number, right? So they are generated randomly. I will not go into the technical details of random numbers, that how we define it. But if somebody is interested, I can again offer you that you can ask for a zero class on understanding the right idea of these random numbers, right? So random numbers basically are not purely random. They are deterministic basically through a function. The thing which we are saying random is the domain of the random numbers, from where we start calculating these random numbers. That domain is random. But the outcome that we get in the form of a random number is determined through a function. So, but this is a very technical detail, so I don't want to go into the detail of the random numbers. But for that, for the sake of argument, for the sake of current understanding, you can just remember that random numbers are randomly generated, and these are the numbers for which you cannot make the 100% accurate forecast. But second thing to remember is that random numbers, they belong to some distribution. This is the fact that random numbers belong to some distribution. They emerge from a distribution, a probability distribution, I mean, from distribution. By distribution, I mean probability distribution. That's why probabilities are important. We don't predict random numbers accurately, 100% accurately, but we can predict their distribution from where they are emerging. Like they might be a normal distribution, it might be a Poisson distribution, it could be an exponential distribution, it could be a gamma distribution, it could be a so on. If you go on Google and on Wikipedia, if you search the types of distributions, so you will find the details in length. There are several types of distribution because every number behaves differently, although they occur differently, randomly, but their behavior is becomes different using the different types of moment generating function or function, the distribution function from which they belong to. So their distribution keeps on varying, what I'm trying to say is. Okay. So in prediction, while using the forecasting models, the important thing is to understand that how we estimate or how we learn that from which distribution the random number belongs to actually. Whether it's a stock return, whether it's a weather forecast, whether it's something else, whatever you want to say. So that's the thing which needs a lot of knowledge and a lot of understanding about mathematical ideas. And we are not obviously not going into that detail. We are just considering normal distribution. You know that we are just considering normal distribution, that our random number belongs to a normal distribution. And normal distribution, why it is used most of the times, it has proves that using the central limit theorem, when your sample starts increasing from a limit, the distribution starts converging towards a normal. So it's safe to use normal most of the times. But what I'm trying to say is that normal is not the only distribution. We have several other types of distribution based on the type of the data. Okay. So, okay, I'm not going into the more technical details of that, but just as a taste that if this random outcome is an X, and I want to say that this is normally distributed. And by the way, this side of your axis is the probability, right? So this is the probability of X. So you can call it f of X as well. Okay, so this is, you give me X, I'll give you this probability. If you give me X, I'll give you its probability. Okay, the region of the probability. And one more thing, just as a gift to you, that in continuous random variable, the probability of any single outcome is always 0. Okay, so the probability that your X would be equal to some constant A is 0. You cannot find out a probability of any single outcome. Keep this thing in your mind, that in case of continuous random variable, stock returns are continuous random variable. So continuous random, and again, these things need detail. I'm just giving you the results. I'm not proving it, or I'm not going into the detail that why is it so. So for that, you need to go back to the set theory. You might have studied set theory in your school. There are unions of sets and intersections of sets and so on. So you need to go into the set theory detail to learn this idea that why the outcome of a single outcome, a constant value, is always so continuous random variable is always 0. If you ask me that what is the probability that stock return would be equal to 5%, so I would say this is 0. It's 0% chance that your profit would be equal to 5%. No. But I can tell you the probability of a return lesser than 5% or greater than 5% or between 5 and 7%. Right? So in continuous random variable, there is always a probability of an area. Keep this thing in your mind. We always need an area, region. For a region, I can tell you the probability. This is true. But for a single outcome, I cannot tell you. This is 0. Right? So that's why we say that X has a distribution normal with a mean 0 and standard deviation 1. And this is called a standard normal. Mind it. If your random variable has a mean 0 and standard deviation 1, which is not the case most of the times or almost all the times, we call it standard normal. But we have a table for a standard normal. That's why we write it. And we write it like this. That is equal to 1 divided by 2 pi square root sigma e to the minus half into X minus mu divided by the standard deviation, where mu is 0 and standard deviation is 1. This is 0 and this is 1. So you'll get this distribution. You just need to give me X, because in this whole equation, only X is a variable. Everything else you see in this equation is a constant. 1 is constant, 2 is constant, pi is constant, sigma is constant. Sigma is constant because this is sigma. Sigma is 1. E exponential constant is constant. This mu is constant because we have said mu equals to 0 and standard deviation equals to 1. Everything else in this model is a constant except this X. And if I take the integral of this, so that would become a cumulative distribution, or you can say that the area under the curve. Okay. Any question to this point? So let's do it in Excel. today I'll show you the Excel exercise. Ready for that?
Yes, sir.
Yes.
Yes.
So here is the Excel sheet.
सर कौन
And
सा बताया आप?
you see my screen?
Yes. Yes, sir.
So the first column gives the date, second column gave the prices. Okay. And the simulation method that we are doing right now is known as Monte Carlo simulation. And I'll give you the detail of it in a bit, right? So we are doing basically Monte Carlo simulation. So we are simulating the data basically, okay? So, okay, this is the data which I have collected from 2014 up to 2015. And this is the price of some company ABC. I don't need to mention the name of the company, whatsoever the company is, right? So you can collect this data from stock exchange. So I have this 2 years daily data. So almost I have 256 observations. And you can do it for anything. You can do it for you can do it for gold prices. You can do it for oil prices. You can do it for anything. Okay. This is just a method of making a forecast. And in this method, we want to know that how this stock price will behave in the future. I have this historical data, almost 256 observations with me. And I want to know what would be the future trend of this data. I want to know the figures here. Let me assume that the time has not yet come, and I want to make a forecast here of the prices, that how this trend will continue. And again, because this is random number, stock prices and stock returns are randomly generated, but they belong to some distribution, and I believe that they belong to a normal distribution. And I have to see that whether this is a normal distribution or not, right? So first of all, I need to make the distribution of it, that how this data is distributed. Okay. So for that, I need to calculate daily returns, daily log returns. So how I calculate log returns? Can anyone tell me?
Sir, log के through जो
Natural log of ending value divided by the beginning value. I told you this yesterday.
Yes, sir.
And I'm going to do it today on Excel. So you see, this is 22nd. This is the ending. So beginning would be this date. I have not mentioned the date here. Definitely 21st September. Okay. So this is the price at 21st and this is at 22nd. So this is ending, this is beginning. So I cannot calculate return here because there is no beginning. But I can calculate return at this point. So that is equal to natural log. Ln function stands for the natural log of ending value divided by the beginning value will give me the log return. Right? So because the price has decreased, that's why return is negative. You can adjust the decimal points according to your own. You can convert them into percentages as well. This is now 0.4791%. Okay. You can again change it back to the normal decimal system. And you can do it for the whole set of data. Okay. So here I have calculated the daily returns. Is it clear?
Yes, sir.
Every return is a log return. Let's say if I check this return, so this is again the natural log of ending value divided by the beginning value. Okay. If I check this is again the natural log of ending value divided by the beginning value. So this is how I have calculated the daily returns. And again, for the sake of your visibility or make it more presentable, I'm just reducing decimal points. And now I want to see that how this distribution looks like. What sort of distribution is it? Okay, how this data is distributed basically. Because I'm not interested in the values, I'm interested in their statistical properties. That what are the statistical properties? Like when patient comes to the doctor, doctor is not basically interested in the patient in itself. The doctor is interested in the medical attributes or the diseases or the medical reports that the patient brings with him to the doctor. So I'm not interested in the data in itself. I'm interested in its statistical properties, because based on those statistical qualities or properties, I can better understand the data. I'm not interested in what type of company is it and what is the business of the company. I'm interested in the stock returns and not on the figures, on the prices of the stock. I'm interested in its statistical properties. Once I know the statistical property, I can make a forecast. I can tell you what would be the future trend. Okay. So now this is the return and I want to find out its statistical property. The first step is to find out its distribution. So for the distribution, I need to tell Microsoft Excel that what type of scale I am using on x-axis. You remember in a normal distribution curve, on x-axis we have x values and it has a scale. You need to give the scale on x-axis. So scale, I'm telling Excel about the scale, and my scale might start from whatever, from 5% positive down to 5% negative. Okay, so this is 0.05, then 0.045, then 0.04, and so on to -5. I want to get down to this -5. Do you understand my scale? This is my x-axis. 0 is in the center. Half, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 5 on the positive side. And on the negative side, half, -half, -1, -1.5, -2, -2.5, -3. And this is my scale on x-axis. You draw the scale on x-axis. Do you understand that? ये एक्स एक्सिस का स्केल बनाया मैंने, सेंटर में 0 रखा है और +5 से लेके -5 तक बनाया मैंने. And I want to see the distribution of this data on this scale. I want to see the distribution of this data on this scale. Okay? So to do this, I'll use the data analysis function in the Excel, and I want to see the histograms. There's a histogram option here. I'll press OK. Input range, what data I am putting in. So I'm putting this data. This is my input data. The returns data is my input data. Fair enough? What is my bin range? This is my bin range. This is known as bin range. When I tell him the scale of the scales on the Excel, on the x-axis, this is called as bin range. So I'm telling my bin range is this. This is my bin range. And I'm not using label right now in the first, so I'm not ticking it. So I want a chart output and I want this output to be here. My output should be here. Okay. You understand this? The input is my data, which I want to plot. Bin range is the scale at which I want to plot. And output range is the cell at which I want the output to show, to appear. And I have checked only chart output because I want to see the distribution in chart. So when I press OK, so it will give me this distribution and a histogram here. So visible to you?
Yes, sir.
So you see, because my data is in very few number, I have only 250 observations approximately. If I start increasing my observation, my data will start appearing normal. It is a sort of a normal, but it is not completely normal, because do remember this thing, that stock market returns are always fat-tailed. This is the quality of stock returns. Whenever you will plot a stock return, you will get fat tails. Tails are fat. This is a very, you can say that, the basic property of stock returns. The stock returns are basically a sort of placer tick. Okay, so they have fat tails, because at any point in time in a stock market, the probability of extremely high positive or extremely high negative return exists. That's why we call stock market returns, they have fat tails. Are you getting my point?
Yes, sir.
Since this is appearing to me as a bit normal, not exactly normal, but I can see that this can be a sort of a normal. And the reason, because this is not looking exactly normal, because if I start increasing, I'll do it later on. If I start increasing the number of observation, or one other thing I can do, I can change the scale as well, because this is a very discrete type of scale here, because I have half and only 1% and nothing in between. So if I add more scale values here in between, means this is less than a half, and then a bit about quarter of 3/4 of one, and then 1, and then 1 and its quarter. If I change the scale, my distribution will start appearing more normal, right? This might be due to the fact that I have used this discrete scale here. Okay, are you getting my point?
Yes.
Okay, now this is the thing that compels me to see that the data appears to be normal. And by the way, I would also like to show you that how exact normal appears to, but first of all, let me complete this. Then I'll show you that how normal distribution appears in the data. So now I have the data, I have calculated its return, I have made up a scale, and I have seen the distribution of my data. So my distribution is, another point came in my mind just now, that whenever you have a real life data, you can make histograms only. You cannot make that continuous curve. You cannot make that continuous curve because you don't have continuous data all the time. It's not possible to collect the data continuously. So you always have discrete values. So we make histograms and try to see whether it appears normal or not. Okay, so there's a difference between continuous random variable and discrete random variable. Keep this thing in your mind. So, but for a data whose nature is continuous, we plot histograms. Histograms are made only for discrete, not for continuous. But because we don't have data continuously for every point, right? So there are so many points missing in between, infinitely large number of points there in between these two, infinitely large points in between these two histograms, these two bars. So we don't have the data, that's why. Never ever, this is not possible even if you have 10,000 observation, even then you will be missing some values on x-axis. So you can't make that continuous curve all the time. So we make histograms and try to see whether it appears normal or not. So I think this is enough explanation for that. And let me tell you now what to do now. Because this is appearing normal and I want to make a forecast and I want to see its statistical properties. So what statistical properties I'm interested in? Statistical. I'm interested in two things that are given by Black-Scholes model, right? So I'm interested in the average of returns. I'm interested in its standard deviation sigma. I'm interested in variance. I'm interested in the drift. Okay, do you remember drift part? Average minus half of the variance in the bracket.
Yes, sir.
That is drift. Average minus half of the variance represents the drift. That thing in the bracket is the drift. And what is the drift? The drift is a long-term trend around which data keeps on varying. Okay, so now let me calculate the average. See, that is equal to average function. I'm using the average function of the Excel. I'll collect the average of this whole data set to 50 around observation. This is my average. What is my standard deviation? So my standard deviation is standard deviation. So the standard deviation of the whole data is here. This is my standard deviation. What is variance? Variance is the square of the standard deviation. So if I take standard deviation and take a square of it, I'll get the variance. Now what is drift? Drift is equal to, look carefully, drift is equal to average minus half of the variance. So variance divided by 2. This is my drift factor. Fair enough?
Yes, sir. Yes, sir.
Okay, now if I have now average, I have the whole drift factor now. What I need to know? I need to know the rest of the part after that part that you have learned previously in finding the price model, right? And that is the part where I need to put in a cumulative normal distribution factor there. Okay, so be ready for that. I'm hiding this data so that you can see the full working there. I'm hiding these observations now so that you can see what I'm doing. Remember, there's a break in this. These cells are hidden, 34 to 254. The cell in between are hidden, but they are present. Okay, I've not deleted them. Okay, now I want to make a forecast from this point onward. I want to make a forecast this point onward. Okay, and you know what my forecast is equal to? I've told you two factors. One is the drift factor and plus some random factor that we have to add. Okay, so that's what I'm doing right now. So you need to watch very carefully what I'm doing. My model that I have studied in the class yesterday, except that was a model to check the probability that your stock price will exceed some given value. Okay, so let me show it again. Let me show that model again. Before putting it here, let me show you that model in the book. This is I'm going to implement in Excel. So this is calculation in practice. That we take the change in the log prices, and then we take two things, the drift factor and the random factor there. And simply, I'm going to implement this model from a Black-Scholes. I'll take the current stock price. Is my screen visible to you, Ji?
Yes, sir.
Okay. I'll take this stock price, then exponential constant raised to the power drift. My time period is 1, so I'll ignore that. Change in time period is 1 day. It is 1. I'm taking it as 1. So I'll ignore this part. Plus, this is technical thing. I'll generate a random number, a random variable, a random outcome from a distribution. This is normal. I'll be using normal distribution, and I'll generating a random number from that, random probability value from that, and multiply it with the standard deviation. Multiply it with the standard deviation. And again, I'll ignore this part because I'm using 1 day as a change in time. Clear to you? Is it clear?
Yes, sir.
Okay. So now let me be back to my Excel sheet. Here I'm doing this. See, remember that formula. That is equal to current stock price. This is the current stock price. Okay. So the current stock price multiply by what? Exponential constant, EXP. And I told you when I write EXP in a bracket, it means E to the power, exponential constant raised. So let me repeat. Let me remove it. Let me start again. So here, what I'm doing, I'm implementing that formula in my Excel. Okay, so that is equal to my current stock price S0. This is S0 because I'm making a model at this point in time and making a forecast for the future. So my S0 multiply by the exponential constant. Now this is exponential constant raised to the power, my drift factor, this is drift, plus my standard deviation multiply by some value which I will take out from a distribution which I don't know. Distribution will tell me in itself randomly. Okay. So how will I'll do this? I multiply by this with a function called norms S inverse distribution. Now let me show you what that distribution is. So here it is. You read this message. This is a function. This function is available for, this is the second line. Returns and standard, this function will return the standard normal cumulative distribution with the mean 0 and standard deviation 1. So I told you that n stands for a cumulative normal distribution. So I'm using that cumulative normal distribution right now. Okay. And what value I will take out from that normal distribution? The z value. So I'm telling the software that I don't know that z value. I want that z value to be picked up randomly. Right? So how I'll do this? I'll give Excel a random function. This is a random function. This function generates random variable from its own. Nobody knows. So I'm giving his z. I'm giving this function z as a random variable. So this is a random variable. Okay. So I need to close all the open brackets now. So let me see once again. So this is, I think, okay. For more safety, I can make another bracket here so that things don't get confused any further. Now this is my forecast. Are you with me?
Yes, sir.
My tomorrow's forecast is 149.2603. And now see the magic. For how long you want to see a forecast? I want to see a forecast over 50 days. I can drag it down and see the forecast. Oops. Something went wrong. Help, help. Okay. Yes, okay, sorry. I did not fix the cells क्योंकि ये जब मैं drag कर रहा हूँ ना तो वो ये भी नीचे आ रहे हैं cells. I don't want these cells to get down with my values. Okay, I want these cells to be fixed. So how can I do this? So I'll go there and I'll see what cells need to be freezed. So this F31 should not move. Okay, when I'll drag the figures, this cell should not move. F31. So where is F31? This is F31. So F31 should not move. Freeze. So now I have freezed F31. Okay. And F33 also should not move because there's a fixed value. So F33 freezed. So these two cells are now freezed. I put dollar signs here. So this dollar sign will freeze the value. Let's see. Now if I drag, yes, now it's fine. Okay. This is my forecast and I need to plot it. I want to see how this forecast looks like. And for that, I'll plot that using a scatter plot like this. Norms distribution is no. We have taken a wrong distribution. Please, sorry. Let me make a correction here. That was an inverse cumulative, if I remember that. That not normal distribution. That was an inverse normal distribution. I have used normal distribution here. Not normal distribution. We need to use inverse normal, if you remember. N to the power -1. Sorry. I used the wrong distribution. Don't worry. This is norms inverse. This is now returns inverse of standard. Yes, this should be the right distribution. I've used a wrong distribution. You see, if you use a wrong distribution, your answers would be wrong. That was an inverse function. Now let me do it. Looks better. And let me freeze my cells from highest to 100 and fix the minimum to, let's say, 100 to look more better. And here you go. Now, from using a normal distribution, I am generating a future forecast. Okay. Let me increase the size of this graph. You see this?
Yes, sir.
Now see, look the magic. This is the only forecast. I could be wrong. And you can ask me, sir, what are the other possibilities? There is another possibility. This could be possible. This could be possible. This could be possible. And you can see in the future, maximum this could happen. You see this?
Yes, sir.
Yes.
Because nobody can exactly predict the future, but I can give you 100 possibilities. And then you can make out a probability that what are the most promising values. Okay. So this is simulation of the data. I have simulated the returns, and this is basically Monte Carlo simulation method. Don't get distracted from this word Monte Carlo. Monte Carlo is a casino in Las Vegas, right? And whenever you use a random number to generate the probabilities, we call it Monte Carlo method. It's not a new method. I've used random number here, okay, to generate a random probability value out of it. These are the forecasts that you can make. So if you tell me what are the 100 possibilities, so one, you are making a forecast at this point of time, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then up to 100. You can make a dots. And then you can draw a new histogram like this from the new data. Okay.
Okay, sir.
So this is the application of that Black-Scholes forecast model. And it has, again, a very wide application in other models as well, other situations as well. Any question? Any question to this point? Okay, so this data has already occurred. That's why these three values are fixed. So I can again do the same thing. I can again make a random values out of it and then stop somewhere at random point and copy the data and then plot it here. I can do it as many times as I like because I am a financial engineer, so-called. Oops, sorry. Control C. Let me do it for 5 values at least. Okay, just give me a minute. Let me copy and paste my data. And 4 and last one is 5th. Now I want to see the trend line here, how it looks like. So you see, what are possibilities in the future? Future possibilities. I have made 5 trajectories. We call it trajectory, and you can make 1,000 trajectories using a more superior software. By the way, Excel is not the right way of making these trajectories because it takes long time, or you need to install some packages in it. Yes, you can do it in Excel as well, but for that you need some adds in. You are not using softwares like R. So I use R to make these trajectories. So I can make in single click, I can ask for 1,000 trajectories of future returns. Right? So any question to this point? Up till this point, if you have any question, you can ask me.